trying to learn that more, and we furthermore, we're trying to push that back to the pre-cancer stage. So if it is true that pre-cancer, in order to become invasive cancer, has to achieve this immune evasion, we should see that at the interface of precancers that either are or are not destined to become invasive. And that's been a big part of our effort to develop the Precancer Atlas. And the Precancer Atlas, although it has a lot of genomic sequencing and RNA sequencing of the epithelial cells, also has a component of studying the microenvironment, and in particular, the immune microenvironment. So we got together, we talked with our immunology colleagues about what were the right combinations. We talked with our technology colleagues about what was the right platform, and we came down to using as the primary platform the Akoya, then PerkinElmer Vectra imaging system, because we thought this was a nice, robust way to do a lot of throughput, which we recognized we were going to need to do, and get really good quality data, although not as highly multiplexed as some of the newer techniques. And we've talked over the series of workshops about how to really optimize and lock down this. We wound up with 2 7-color panels for immune cells and immune cell infiltrates around tumors. And we've studied that in the Precancer Atlas project. We've studied that across other tumor types, working in collaboration across the consortium. And it really has been a true cross-consortium collaboration. We learned along the way a lot of things, and we talked about a lot of these things along the way. We learned that there were details related to how that microscopy gets performed, gets constructed as a digital image or a multi-layered digital image. And we had the very fortunate foresight. I'll give Angelo credit for getting Alex Zalay on his grant. So Alex Zalay is part of the MCL consortium formally from the beginning as a part of the Hopkins prostate-based grant. And he has developed, taking his astrophysics experience, developed methods, which we're going to hear about today, for improving on how we reconstruct and then deconstruct the elements of the tumor immune microenvironment from these multiplex digital images. We have talked a lot about other platforms and software that we can use to do the analysis. We've learned that the analysis is, in fact, still the bottleneck. We can create the images, stain the slides, create the images, but the analysis is still slow and requires expert attention throughout the process. And so with that in mind, we thought we would explore newer analysis methods today, including application of artificial intelligence and machine learning methods. We have employed machine learning methods along the way, but for specific tasks like cell segmentation or tissue classification. And we have not really gone beyond that, but I think it's time to think about that. I think for our AI colleagues who are either on the phone or will be coming on to present shortly, beware, this group tends to be skeptical. We will kick the tires pretty hard and try and figure out what the limitations are, what are the questions we can ask, and that's the goal for today, really, is to do just that. We'll have a series of talks. The ground rules are that this is a workshop, so I encourage you to interrupt in the middle of the talk and ask questions. We have dedicated time so that we have time at the end. We can ask questions at the end, but we also have time built in. We can ask questions as things go along. If that starts to get out of hand, I will appoint Angelo to wrest control and limit the questions. I'm not very good at limiting questions, so that's why I'm pointing Angelo. But I do encourage you to ask questions in the middle, and you can do that either by unmuting and breaking in, or you can raise your hand, however you want to do it. You can put a message in chat. I'll be monitoring chat. But this is supposed to be a dialogue. We're supposed to be using the PowerPoint presentations just as a starting point for discussing what we want to get out of this. So I encourage active participation from everybody participating. No question is a dumb question, so please speak up. What am I forgetting, Angelo?
No, that's a great introduction. And yeah, we did build in each speaker, almost every speaker. I think Alex today, we gave him a little bit more time, but all the other speakers have 20 minutes to present, but we have 15 minutes for questions. So it really will be interactive. You know, we may get late on some, but maybe catch up on others, but nevertheless, it's definitely meant to be interactive. So I'd say, let's go.
All right. Do you want to pop up the share screen and pop up the agenda, Angelo? And
I'm going to have to get off the call a little bit, so it may not be best if I do that. But
all right.
the first person we have is from Visiopharm, Brit Boehmer. I may be saying that name wrong, Brit. If you're on, please.
All right. We are sharing. Excellent. And it looks like we're recording. Great. So anybody speaking, if you want us to stop the recording, please let us know, and we can stop it transiently if you're going to talk about unpublished data that you don't want recorded. The recording also can be embargoed for a period of time if you ask us. So you can leave it in, but ask us not to share it publicly for a period of a few weeks or whatever you ask. So let us know about that as well. But as long as you're comfortable with it being recorded, we're going to record the whole session.
Yeah, please do. I'm happy to start off our conversation today. A little introduction. My name is Brit Boehmer. I spent several years as a postdoc and then an early faculty member at the University of Colorado's Anschutz Medical Campus. My focus was in pediatrics, and I gained considerable exposure. I was basically gifted the histopath facility at the Perinatal Research Center and asked to modernize it. So in that process, we onboarded new staining protocols. We optimized methodologies across the entire process. We onboarded high throughput multiplex imaging capacities. And that was also my first introduction to Visiopharm, and I became a power user. I'd also like to introduce my contemporary, James Nurple. He's the Director of Sales for the West Coast, and we're happy to share a little bit about Visiopharm's deep learning algorithms and applications with you today. To start, Visiopharm is an image analysis company, and regardless of the imaging modality, regardless of the complexity of your image in terms of multiplex, singleplex, our concept behind the platform is to make image analysis easy and robust. A little bit about the company and its background. We are one of the longest standing image analysis companies in the world today. We currently are comprised of 95 employees. Most of them have advanced degrees, and about 50% of them are engaged in either front-end client support, so helping to onboard new customers, clients, or continuing support, say 5 years down the road, and you run into a challenge developing an algorithm. The other part of that is developing the next revision of the software, of which we release about 3 to 5 each year. We are proud of the patents that we hold on our platform, and we're well balanced across both academic, big pharma, CRO, and biopharma companies. We are at our heart a technology and AI company. We do offer 120 or more ready-to-use algorithms. 8 of those are in the European market as CE-IVD apps, and that sets a threshold and a precedent for the approach that we take in the uniformity of our algorithms and their ability to handle robust data sets, as well as speaking to the regulatory compliance that we aim for. It should also be an indication of our trajectory here in the United States as well as Canada in terms of where we're headed in the near future. 100% of our software is rooted in AI, and I'll circle back to that in just a few moments. We're also well aligned with the multiple partners that you probably utilize in your laboratory environment and trust as your partner there. Just a brief introduction of our US West Coast team. Amanda Lau is our managing director. Esther Abel was recently brought in as our chief clinical and regulatory officer. I've introduced myself and James. We also have a technical sales specialist for the diagnostic clinical sector in Jenny Caldera. And we have an entire team of professional services member support staff that is there to not only help users onboard into the platform, but ensure continuing success as your needs mature through time. As I mentioned, artificial intelligence is the foundation of everything that we do. We provide a powerful AI toolkit that is really robust in its approach. Of course, we have machine learning components extending from the simple thresholding up to more complex decision forest types of approaches. But recently, we've added on a deep learning component with 3 different convolutional neural networks that are really centered around ease of use and the thorough and accurate evaluation of complex challenges. The reality of artificial intelligence, specifically deep learning, is that it's not magic. Automation doesn't necessarily result in an augmented data set. Starting with your image, which is a representation of the raw data, it doesn't go into a magic hat and then immediately come out as data. Pardon me, sorry. It doesn't come out as data that you can readily use in your research or clinical facility. Instead, it looks a little bit more like this. And Visiopharm's approach is to simplify the process to augment your analyses. We start with an enriched data set that is enriched through annotations, and those annotations can occur either through machine learning algorithms or through the robust training annotations provided by trained staff members. From there, we'd start training the convolutional neural network. And then after that's trained, that begins a review process to ensure that the algorithm is functionally competent, or to return it back into a scenario for additional training. And it's only after that process that the results can be viewed in an accurate and comprehensive manner for a research or diagnostic lab. Again, our approach is to make deep learning as easy as it possibly can be from both an image analysis or a tissue mining perspective. Starting with your original digital stain, we apply a number of deep learning algorithms to interrogate difficult features, including glomeruli segmentation, node metastasis, tumor segmentation, and nuclei segmentation. Now, all of those types of algorithms are part of our ready-to-use AI-assisted apps that you can download freely from our online platform. That said, the unique thing about Visiopharm is that we provide you an author tool that helps you to build individually tailored solutions to your complex problems without needing any programming experience. And when it comes to deep learning, this process can be as simple as just tracing the outline of your feature of interest. Next, I'll introduce the platform just briefly to show that it really is an easy to use and integrated toolbox for any range of image analysis problems. Starting with the core platform, we have the entire toolkit that is meant for building apps across imaging modality and file format. Our deep learning classifiers are integrated into the AI author, which means that they can be used comprehensively across the entire platform and exchanged with machine learning approaches applied in the many different modules that we offer. Additionally, the outputs are fully customizable, and we do offer an app center, which I actually prefer to call the inspiration library, because it gives you an insight into how our experts develop algorithms from workflow to specific post processing steps in order to help you learn and maximize your efficiency within the platform. From there, we apply several modules to extend the functionality of the core platform, including a tissue array module that de-arrays cores for individual analysis, one of the most comprehensive multiplex phenotyping modules for automated unbiased clustering of multiplex data, a tissue align module that allows co-registration of serial sectioned or serial stained images, even if they're in different modalities. And of course, brain mapping, which can be utilized either using a brain atlas or, in my experience, more robustly, using a deep learning algorithm to look at those brain regions. To step into app development just briefly, we utilize a train by example type of methodology for training a deep learning algorithm. Here, examples are provided, and the network is built to optimally differentiate them using any of the available features. Features can be annotated by hand, just tracing the different areas like necrosis, stroma, I got stroma and tumor back switched there. Or you could use machine learning to get the rough outline of these areas and then train from there. And of course, any of these examples can be trained on single or multiple channels in order to provide the accuracy you're looking for. We can also do robust feature differentiation because we're able to use any of the available features within Visiopharm, as well as the intrinsic textures of the raw image. And then after the deep learning app has been developed, it can be augmented in multiple ways, either by passing it through to a threshold classifier for further refinement, or by cleaning it up using any number of post-processing steps.
So Brett, I'm going to interrupt you right there.
Yeah.
So when you do that training, maybe go back to that slide.
Sure.
One of the issues that we've had is that we want to be able to define or classify, the tissue type in the section, but we want to ensure that we're unbiased to certain channels.
Sure.
So a good example is breast cancer with estrogen receptor, and you want to be able to identify the breast cancer, but if it's a pretty strongly estrogen receptor positive one, the training algorithm may look for that unless you specifically tell it not to. So my question is, can you assign sort of channels to exclude from the classifier, or pick a channel to include to avoid that bias?
Yes, most definitely. Within the app author tool, there's an additional component called the AI architect, and that allows you to plug into the convolutional neural network that you've selected. From there, you can modify the number of channels or select the channels that you'd prefer the convolutional neural network be trained on. So in the case that you're looking at a highly ER positive breast cancer tumor area, you can preferentially exclude certain types of areas. From my experience, however, the platform is robust enough that even with lobular or differentiated types of tumors, especially given our basis in breast cancer in particular in Europe, the algorithm for tumor detection, for example, has matured to a point where it's able to look beyond the individual biomarker expression and into the actual tumor architecture itself in order to define those boundaries.
Okay, thank you.
Certainly. Any other questions before we proceed forward? Okay. The deep learning training actually develops its own feature. And I'd like to highlight that using a nuclei segmentation approach. Here we have a native DAPI channel that's indicating the nuclei in this IF image. From here, what the convolutional neural network is actually learning is more like a positivity ratio, where we're looking at white being equivalent to 0 and black being equivalent to 1. So if you think of it as a probability scale, we're able to differentiate the background from the nuclei, but we're also able to add in additional features like boundaries around the nuclei, which then allow us to have one of the most robust nuclei segmentation approaches in the marketplace today. And it also helps us to then expand these nuclei into cellular boundaries, especially when augmented by a membranous channel or one or more membranous channels in order to create an environment to do multiplex phenotyping, for example. Of course, in the App Center, we provide algorithms for nuclei detection, both in H&E, IHC, and fluorescence space. Before we continue on, it's important to note that commonly you think of these as our releases of these algorithms, but in truth, these all started with a research question. One of our users contacted us, typically from the academic space, and said, "This is a challenge I'm running into. Can you assist us?" Our experts worked with them to generate these, and then for a reduced cost, we were able to publish these algorithms. And that's the origin of the next several algorithms I'll show you. After you've identified the nuclei in your sample, you can then interrogate the nuclei quite robustly. And I've provided just 3 examples here. There are actually many more, but these represent the diagnostic offerings that we have, or translational in the US, for ER, PR, and Ki67, where we can look at either a positivity or we can do H scoring or some other scoring mechanism on those nuclei according to things like intensity or size. From there, of course, because oncology is a huge area for histopathology, we've developed with our academic partners algorithms for metastasis detection or invasive tumor detection. We can do tumor detection in IHC as well as H&E. We can then interrogate those, say for a PD-L1 positivity evaluation in a lung cancer. We can also extrapolate beyond just the oncology field to look at PD-L1 germinal center isolation, and even liver fibrosis in Mason's trichrome, or as the example here indicates, PSR. But I thought it'd be interesting to step into an actual use case application for one of our large pharma partners. Their workflow was that they wanted to look at the GI tissue in order to determine regional biomarker expression. Using the comprehensive AI toolkit, we first apply a machine learning approach to identify the primary tissue area, and then we apply a deep learning convolutional neural network to evaluate the mucosa area, the villi within the mucosa, the submucosa region, the muscularis, and the submuscularis. After they've been identified, we can regionalize them using regions of interest and interrogate each one of those independently. From there, we can interrogate those regions looking at CD31, CD38 in this example in the chromogenic space in order to get a highly accurate assessment of each one of those biomarkers, despite the similarity of the chromogenic stains used. We're also able to provide a comprehensive nuclear assessment to augment this in order to provide an idea of what the nuclear density or cellular density is in each one of these areas. To dive into the GI tract tissue segmentation, I provided a few screenshots of what that might look like, or what that did look like in this case. And we are not only able to regionalize each area quite specifically, but as you look into the other panels, you can see that the segmentation occurs on almost a pixel level basis. When we showed this to our industry level partner, this was a paradigm shift in how they approached their analysis moving forward. And then of course, no analysis would be complete unless we actually evaluated the biomarkers themselves. And here we've got an indication of the different nuclei and the segmentation, even if they're closely related or overlapping, as in the case of several of these. When we asked our industry partner how they were performing this previously using their other toolkits, we found that our approach tended to give them more accurate representations relative to a manual count and save them considerable time, because this is a process that we can easily automate. Additionally, we can perform marker assessments here for CD38 and CD31, and we can differentiate them on the same run so that you can have a comprehensive analysis with a full analytical report out at the end. In this case, we were able to report not only the spatial relationship of the biomarkers to one another within a region, but we were able to report out areas, diameters, and counts for each individual biomarker.
Your dog says you deserve some credit for that.
Yeah, of course. I apologize for that.
No worries.
But so I hope you've seen just a brief overview. I'm certainly happy to dive in a little bit more to our deep learning approach and how that would augment the workflow in things like multiplex phenotyping, or how the other toolkits would be empowered using our deep learning algorithms. Thank you for your time, and happy to take any questions you might have.
All right, the floor is open.
Looks really good. Thank you for doing that. Just one quick one. That image on the right looked like, I couldn't tell what they were, but we have an issue trying to measure like dendritic like cells or macrophages or dendritic cells, and counting them, I think for almost everyone, and maybe Cliff can also get at this and others, is pretty challenging to tell what's a cell. Sometimes there's little spikes coming in and out of the plane section, but are you guys able to deal with that? I know lymphocytes are pretty easy, you know.
Sure. We've actually done numerous different cell types, as you can imagine. Macrophages are one of those things that we're currently working with several partners to evaluate. Every analysis that I've seen so far is highly accurate and very sensitive. Even extrapolating this into the neuro field, where we're looking at astrocytes that in a 2D image, the dendrites can go in and out of the plane.
Yeah.
The deep learning algorithm is able to extrapolate where those dendrites do go in and out of the plane and make an association between two seemingly unrelated parts of the dendrite in the IF field, and then create the linkage between them so that you have one complete astrocyte. And so in both of those cases, the deep learning performs really well, and the time for development is considerably less and much easier to do than applying a machine learning approach.
Yeah, sounds very cool. Thank you.
Any other questions?
Can I ask one? So when you have the marker negative tissue or the normal tissue without having the marker positiveness, can you still recognize it as a normal or the tumor area for the tissue segmentation?
Yeah, no, that's great. in the case of how we approach training a convolutional neural network for a deep learning algorithm, it is possible to include normal or negative tissue. A recent example was we were working with a vet diagnostic lab that was looking at Scrapie's expression. And they provided us several tissues, both across the range of positivity, but also neutral or negative, so that we could show that the positivity could be related to the relative expression. The same thing is true in normal tissue when evaluating tumor area. And I actually think that including those negative or neutral normal tissues can be a great positive when it comes to training these algorithms, so that you have something that can handle the variation that a real world sample set will actually have.
Thank you.
So one of the things I like a lot about you guys at Visiopharm, first of all, you know, from my perspective, I'll just go out on a limb and say that I think that for the image analysis platforms that have been around a while, and I won't name them all, I think Visiopharm is sort of the Cadillac in some ways. You guys have one of the best, most robust computational products out there. It's also not inexpensive to get into, but and not trivial in terms of learning curve from what I've seen. But I like the fact that you also are building these defined algorithms for clinical use, because one of our goals here has long been trying to bring research into translation for clinical care and improve clinical diagnostics. So maybe you could talk a little bit about how you take something that's so flexible and has a steep learning curve and kind of dumb it down for the regular user in the clinic.
Sure. Yeah, that's a great question. I'm glad it got brought up. Our approach at this point starts very early in the process. We initially work with the histopath lab for clinical pathology. We calibrate the algorithms, each individual algorithm, to the specific stainers, to the specific scanners that you're using, so that the algorithms are highly tuned and very standardized to your specific location. Then from there, once the algorithms have been trained both on standardized sample sets as well as real sample sets from your facility, we then would lock down that algorithm. And then from there, it becomes a simple workflow where any pathologist, any technician can quite simply go into the system or into Visiopharm's platform, load the number of images that they want to run on that given day prior to readout or sign off, run the algorithm with about 3 clicks of their mouse button. They'll come back a short time later and review the markups within the visualization window of Visiopharm. And we've really worked hard to streamline that workflow so that algorithms can be loaded and run on a batch of samples within minutes. Does that?
This is,
Go ahead.
This is Mehdi the Maggie from Moffett. We actually have Visiopharm at Moffett. I've been not very happy with it. You know, what she says is, he said it's possible. Yeah, it's possible. But for any optimization, first of all, it takes forever. And you need a lot of like technical, I mean, it takes a lot of technicality issue, and then you have to go back to the developer because it's not open, you know, open source. And then, yeah, I mean, I have to like switch actually to other, like, you know, to custom build, like, you know, algorithm for our analysis. So yeah, it's nice, but if you actually use exactly what they did and what they use for training, wow, and then use exactly the same, you know, for your analysis, which is not the case, you know. We always like deal with different sample size and different type of samples. So
now,
yeah, and for anything,
I think you guys are saying
input,
the same.
they're gonna charge you. Yeah, for any, like, you know, they say like, okay, it's a multiplex, I mean, analysis. Now you have to buy like a separate package. it's a different type of analysis. You have to buy separate package, you know. So
I think you guys are actually saying the same thing, right? Which is it takes a lot of development to get something to lockdown stage or to be super user easy. And in between the development, as I alluded to, is a steep learning curve. And it sounds like in order to get that to the next step, the experience so far, and correct me if I'm wrong, Brit, has been that it requires working with your team that's the most experienced at using the product to get things to the lockdown stage. I guess I just want to extend the question a little bit, which is once you do get through all of that work, which, you know, Mehdi, to his credit, is game to try any new platform and tackle the learning curve. But he's much more on the research side than the clinical side. So he's looking for solutions that get him good, robust research data. And I think that those can be had here. But my question for you guys, and we need to move on. I'm getting a note from Angelo. Thanks, Angelo. When you do get it to a lockdown stage, like you showed the ERPR and KI67, do you also have plans, or have you gone to the FDA for clearance of that? What's the story on that?
Sure. We are currently in the process of navigating things with the FDA. As you can imagine, that's not a short-term process.
Yeah.
And so that is in the works. That's part of the reason why we brought Esther Abels on board as our Chief Regulatory Officer.
I got you.
That said, we will have internally validated clinical deployment, or I should say translational deployments, excuse me, reported in sources that you guys will be very familiar with, and at institutions that you are probably collaborating with before the end of the year. And there will be multiple institutions.
So there's obviously for ER and PR and even HER2, there's competition in that space. But what we'd be looking at in this consortium primarily is these panels that we've worked on for 4 or 5 years, Immune Panel 1 and Immune Panel 2, as they're referred to these days. Right now, our image analysis is the bottleneck, and we're definitely looking for ways to speed that up and turn that into something that could be locked down and used clinically and reported clinically. We think it's going to be important. We have to prove that. But anyway, I'll leave it at that. And I want to thank you guys for presenting. That was a terrific introduction to our day.